Why does ketchup refuse to come out until suddenly it explodes everywhere? Why can some liquids behave like solids? And why does toothpaste stay on your brush instead of dripping into the sink? Today, we are entering the strange world of fluids that break Newton's law. Some fluids remember the force you apply to them. In fluid mechanics, most students think fluids are simple. Water flows, oil flows, end of story. But in reality, fluids can become thinner, thicker, elastic, or even temporarily solid depending on how you apply the force. And understanding this behavior is critical in chemical engineering, biomedical systems, food processing, cosmetics, petroleum industries, polymer manufacturing, pharmaceutical production. This field is called rheology, the science of flow behavior. Let's build the map of fluids. At the simplest level, fluids are divided into two parts or two main classifications, the Newtonian fluids and the non-Newtonian fluids. Newtonian fluids are predictable, they follow or they obeys the Newton's law of viscosity. Viscosity is a fixed constant, no matter how hard you state them. But non-Newtonian fluids are a bit different. Their viscosity changes with shear rate, applied stress, or even time itself. And that's where things become fascinating. This is the point where everyday intuition about liquids completely fails. If we talk about the Newtonian fluids, the example could be water, air, ethanol, most light oils. These fluids behave consistently and predictably. But once we talk about the non-Newtonian fluids, their viscosity is not constant, as you can see here, that some of them become thinner when stressed, some of them become thicker, some need a minimum force before they even start flowing, and some literally depend on time. This means viscosity itself becomes dynamic, and this single idea explains the behavior of blood, paint, toothpaste, shampoo, mayonnaise, chocolate, etc. Basically, most real industrial fluids are non-Newtonian. In engineering practice, Newtonian fluids are actually the exception, not the rule. Now, if we talk about the fluids type, that Newtonian, and the second type is non-Newtonian. Among these, there are time-independent, which includes pseudoplastic, dilatant, Bingham plastic, time-dependent, which means unsteady state, thixotropic, rheopectic, and once we talk about the viscosity effect, viscoelasticity, then elastic and viscous properties. So these are the fluids that are included in these. So the time-independent fluids that the shift to apparent viscosity, the time-independent fluids displays steady state rheological behavior. Their shear stress depends entirely on the rate of shear, regardless of how long the shear is applied. Accordingly, that mu is replaced by eta, the eta substitution. This is the viscosity, while we replace mu, constant mu, with eta, which is the apparent viscosity. And the fluid classification now depends entirely on how the value of this eta behaves or changes with the change in the shear rate. Now we talk about the pseudoplastic fluids, that the first type which we are discussing is pseudoplastic, could be also called as shear thinning fluids. These fluids become less viscous when shear rate is increased. Or in simple words, the harder you stir, the easier they flow. Why does this happen? Because their internal molecular structure begins aligning in the direction of flow, reducing resistance. There are different examples: polymer solutions, greases, starch suspensions, detergent slurries, biological fluids, and mayonnaise. This is why ketchup suddenly rushes out after shaking the bottle. This behavior is extremely useful industrially because pumping becomes easier at higher flow rates. Talking about the next type, which is the dilated fluid, opposite of what the pseudoplastic fluid was, that it is shear thickening. It becomes more viscous with the increase in the shear rate. It means the harder you apply the force, the more solid they can become. The examples include corn flour sugar solutions, wet beach sand, potassium silicate in water, and there are different examples which you can see here. At higher shear rates, suspended particles jam together and resist motion. This is the same physics that allows people to run across a pool of non-Newtonian fluid. Fast force creates resistance, slow motion creates force. Now talking about the next type, which is the Bingham plastic fluid. Some fluids refuse to move at all unless you apply sufficient force. So for such type of fluids, we call them or we classify them as Bingham plastic fluids. They require a minimum stress called yield stress, as you can see here, before they can start flow. They behave almost like solids. Above it, they start moving. So you can see that this is a solid representation. Once you apply the stress, then they start moving or behave like a fluid. So here their pattern is a bit solid and then they flows. The examples include drilling muds, peat slurries, chocolate, toothpaste, paper pulp, and sewage sludge. Your toothpaste is secretly pretending to be a solid. Now talking about the next part, or before going to that, you can see dilatant fluid, pseudoplastic fluid, Bingham plastic, and this white line is the Newtonian fluid representation. So you have to understand this behavior between the shear rate and the shear stress to identify which are the Newtonian fluids. These three are the non-Newtonian fluids, and the ideal fluids is represented by this one. Now going to the time-dependent fluids, which shows the unsteady state behavior. The previous one were the time-independent, but they were shear-dependent. This one, the time-dependent fluids, there are two major types, thixotropic and rheopectic. For these fluids, shear stress alone is not enough. Time itself changes the viscosity. Now the impact of time, if we see here, for the thixotropic versus rheopectic, that under a constant applied stress, with the change in time, the apparent viscosity changes. Now for thixotropic, which is this green line, that the decrease in eta or the apparent viscosity over time, the examples include shortening, food materials, paints. While for rheopectic, the opposite behavior, that the value of apparent viscosities increases with time. Examples include gypsum suspensions, bentonite, clay. So this is the overall representation of these two fluids. Next one, the third type is viscoelastic fluid. These materials behave partly like liquids and partly like elastic solids. They can flow like fluids and store elastic energy like solids. So these have dual behavior, like they can behave like fluids and behave like solids as well. So you can see this is at rest, then you have applied the stress, and then the stress is released. Fluids that show both viscous flow and time-dependent elastic properties. The examples include flour dough, napalm, polymer melts, and bituminous. A viscoelastic fluid doesn't just flow, it reacts, remembers, and recovers. So if we talk about the diagnostic matrix for all these fluids, if you classify Newtonian, pseudoplastic, dilated, Bingham plastic, thixotropic, rheopectic, and viscoelastic, the effect of apparent viscosity with shear rate, Newtonian fluid is obviously the constant value. For pseudoplastic, it will decrease. For dilatant, it will increase. For Bingham plastic, constant. And for thixotropic and rheopectic, it will remain independent. And there is not applicable for viscoelastic. Versus time, no effect on Newtonian, independent for pseudoplastic, dilatant, and Bingham plastic, while for thixotropic, the value of eta decreases with time and rheopectic increases with time, and this is time dependent. Yield stress required, so obviously it is yes for Bingham plastic. And these are the examples which we have already discussed one by one previously. So coming to our final point, that Newtonian's law is not wrong, it's simply a small part of a much larger reality. Real fluids are far more complex. They can thin, thicken, resist flow, depend on time, store energy, and even behaves like solids. And that the complexity is exactly what makes transfer phenomena so fascinating. If this video changed the way you think about fluids, make sure to subscribe because upcoming lectures will dive deeper into momentum transport, velocity profiles, boundary layer behavior, advanced rheological models, real engineering applications. And before you leave next time, ketchup refuses to come out of the bottle. Remember, you are not fighting the bottle, you are finding the rheology. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.